Okay, for the sake of simplicity of notation, let me use the following notation. We will be representing this portion of the matrix by A this portion will have rectangular matrix that represents gradients working on the pressure field. Will be, sorry, not P, but B. Let me denote this part by C. And we already know, because I've mentioned that C is basically the transpose of B. And let's start derivation. First, let's start not with the simple algorithm, but something that is very, very naive. Let's write the equations exactly how they look. It's, okay, let me call Vx and Vy as U in general. Then A times U plus B applied to pressure equals some right-hand side vector, generally the momentum sources. Then we need to discretize the divergence constraint, which would be C times U equals 0. Now, what can we do with that? We can use the first equation to calculate what is U analytically. U is F minus B times P, and then let's take the inverse of the matrix. Okay? And since we already have U, let's plug it to the second equation. Then we see that C, A to the power of minus 1, F, minus C, A to the A inverse B, P equals 0. What's the unknown? The only unknown is the pressure field. The pressure field that we need to have to satisfy all the constraints, the equality constraint stating that the divergence of the velocity field is 0. So we can write C inverse of A, B, P equals C inverse of A, F. Knowing that C is actually B transpose, we can write it B transpose the nice thing about this matrix, the very nice thing about this matrix is what?
It's symmetry and positive defined.
Turns out that this matrix is symmetric, positive defined. So we already have many, many solvers that we can use to solve this matrix. Now, let's try to imagine how the solution process would look like. Well, we need to generate the right-hand side. So let's assume we know the source terms. That's good. We've got the vector. That's nice. And, inverse of A, what does it mean? Inverse of A times vector means solve such a system of linear equations. Yeah? Like x equals B, then x equals, inverse of A times B. So having something like that means, okay, solve this system for x. Okay, that's good. And it's not so bad. Like, we do know these matrices. They are not symmetric positive defined. They are something, but at least they don't, this matrix does not have this 0. So we have many, many solvers to use to solve it. Okay, we've solved that. So the solution is a vector. C is that, no problem. I've got the matrix, I've got the vector, I can calculate that explicitly, step by step. That's good enough. Let's touch that. What do we have here? This is something that we want to solve for. And the matrix of the linear system is that. Okay, we've got B. The inverse of A. Not really. Not really. And we can't really have it. We maybe can prepare the inverse for a couple of hundreds of unknowns, but no, not if we've got a mesh with 1 million unknowns and equations. And then, well, multiply by some other matrix. So we can't really generate it. We can't really build it explicitly on the computer. What can we do to solve such a system without having this matrix constructed explicitly? Can we use some of the linear solvers?
I have two ideas. I don't know which is better, but we can, let's say, do it one by one. So in first step, divide by B transpose. Later, multiply by A and divide by B. So let's say we are taking this matrix step by step. It's sometimes the idea, not always.
What do you mean divide by B?
Multiply by B to the power of -1.
So that
it's a rectangular matrix, so it's not always linear, but it can work sometimes. And the other idea is just, I think, approximate A to the power of -1 by, I don't know, diagonal or something.
That might be a good idea. But first of all, starting with the direct algorithm, I mean something different. If you remind any Krylov subspace solvers, I mean, for example, conjugate gradient method is one of them. Conjugate gradient method, B conjugate gradient method stabilized, GMRS would be the same. If you use one of such solvers, then these solvers, the only matrix operation, the only operation inside of these solvers that involves the matrix is taking the matrix times some arbitrary vector, and you need to be able to return the vector that is the result of such a matrix vector multiplication. For the conjugate gradient method, B conjugate gradient method, GMRS, you don't need to explicitly have the matrix. You only need to construct a procedure that is able to give the result of matrix vector multiplication once this algorithm gives you the vector V. So that's already something, because what you can do is, okay, we need to solve the problem with such a matrix, and we can't build the matrix explicitly. So what do we do in the iterative solver? We start with some approximation, and we need to multiply whatever conjugate gradient gives us we need to multiply this matrix by this vector that we get from the conjugate gradient, and we need to return the result to the conjugate gradient. Okay, so how do you construct such a multiplication? Assume you got some vector v. So what you do, well, let's follow the order of matrix operations. So you basically calculate b times v. This can be done, no problem. Well, right now you've got b times p, b times v. So the next operation is multiply on the left-hand side by inverse of a, which means solve the system of linear equations with a. Well, again, not a perfectly beautiful operation to be done, but something that can be done with some other solver. Okay, we've got the result. So multiply bt by the result, and that's it. Voila, we've got the result that we can return to the conjugate gradient method. So we've got the result that we can return to the conjugate gradient method. And see, this would work and this would finish the solution procedure. What's the problem? Here, to generate the right-hand side, we need to solve the system of linear equations with the matrix A. We did it once. Okay, not a huge problem. What's the problem here? We need to run the conjugate gradient method that will do its iterations, typically 50 to a couple of hundred iterations for the real physical problem. And in each iteration of the conjugate gradient method, we need to perform such a matrix vector multiplication. And each matrix vector multiplication, in our case, means we need to solve a system with matrix A again. So solving such a problem requires actually solving a problem with matrix A like 500 times maybe, if you've got 499 conjugate gradient iterations. Expensive, very, very expensive. Nevertheless, it can be done. What's the next problem? We
need to update A because...
Exactly. We've just solved the linear system. And Navier-Stokes is not linear. It does involve the convection velocity. So we've right now solved the linearized Navier-Stokes equation for the current velocity and pressure, but it was linearized, so we need to update the velocities, take the new velocities to the convective term, construct the A matrix again, and iterate the nonlinear terms. Good luck with that. It works. It works. For small problems, you can write such a code. Nice numerical example. I think it's even on one of our tutorials, of the CFD Toolbox tutorials.
What is linear and nonlinear?
What is nonlinear? Nonlinear is that, because basically if you got Navier-Stokes, then the matrix depends on you because the convective term depends on you. What is linear? Like, what is linear? You are actually only using the linear solvers for linear systems. So, so you need to assume some velocity approximation to construct C. So you're working in the matrix with constant coefficients.
That's only to construct A, or that's only to construct A, inverse of A.
No, generally the solvers for linear equations are much more efficient than any of the nonlinear solvers. So you want to be dealing with linear problems, not nonlinear problems. And you're solving the nonlinear Navier-Stokes problem by solving a series of linearized problems. So unfortunately, you need to approximate the advection velocity somehow, construct the matrix with constant coefficients, solve it, and, well, go ahead. A lot of work, not very nice. So people have come up with the idea of the simple scheme. And the simple scheme is, well, commonly used in fine volume method. It's, for example, used in ANSYS Fluent. There is also, if anyone is interested, in tutorial 2 on our Quickersim website, tutorial 2 for CFD Toolbox exactly shows how the simple method works. Let me go through that right now. The simple method does a very important simplification. Again, it starts with the same discretized problem, and what it does is, well, first of all, let's assume that you make initial guess, let's call it P star. And this can be whatever. We will keep improving this approximation to get real physical pressure. So assume we've got the initial guess P star, and then we want to get initial guess for U, which would be U star, and we do it exploiting this equation. So basically we are using P star to calculate U star as something like that. We've already discussed that. This can be easily calculated. This one requires solving the system of linear equations once. That's okay. And we've got the initial guess for the velocity field. What have we got then? Then we've got we make the observation that this set of equations is not really written for some initial approximation. What it's written for physical correct velocity and real physical correct pressure. So we make the following observation. Okay, let's assume that the physical correct velocity is our initial guess plus some correction that needs to be done. Same with the pressure. Correct pressure is our initial guess plus some correction that we need to make to the system. Okay, let's see. This system of linear equations is written for U and P. We have made some initial guess P star at the beginning, and using the equation, we have calculated U star. So already we know that P star and U star also satisfy this equation. Right? Evident or not? Yeah, we've used this equation and we've plugged P, so U, if we solve the equation properly, then U certainly satisfies this equation as well. Okay, so subtracting the equations, means that what also fulfills the equation? Exactly, u prime. U prime plus b p prime equals f as well. Now, 0. Right. What have we got here? We didn't exploit this equation, so still we need to write that the physical velocity satisfies that, because U star does not satisfy the divergence 3 condition. Okay. And let's untangle that again. Right now we want to do the following, namely, right now we are making the most important approximation of the simple scheme. The simple scheme because, well, if we use this equation to solve for correction of U by moving this one to the right-hand side and multiplying by the inverse of A, and then we would plug it in here, we would end up with the same problem that we had a moment ago, right? So we can't afford that. So the most important approximation that the simple scheme does is it replaces this equation by d times u prime plus b times p prime equals 0, where d represents only the diagonal terms of the matrix A. Only the diagonal terms. That's nice because in the previous case, when we need to calculate the inverse of A, then if it should be the inverse of D, and well, it's just the inverse of each element on the main diagonal. That's extremely cheap numerically. It has got its own physical interpretation in the defined volume method. If we are, okay, let me use the staggered grid approach. In the defined volume method, if you're discretizing the equation for the y component and you're drawing such a finite volume, then dropping the other terms means dropping everything that is associated with the viscous terms and only representing the probably part of the convective term, part of the diffusion term, because also it also contributes to my coefficients, but it does not relate directly to the velocities at the neighboring components, and it does still include the inertia. So to say, we see that it drops some portion of the diffusion and leaves me with the other phenomena. Once this approximation is done, we can now say U prime is nothing else than, well, minus d to the power of minus 1 b p prime, and let's plug it in here, which is C U star minus d to the power of minus 1 b p prime equals 0 Then we have C inverse of D, B, P prime equals C E star. And let me comment that. Again, let me write C is nothing else as B transpose. Again, here we've got the matrix which is symmetric, positive defined. Right now, the good information is that we explicitly have got B. D is the diagonal of A, so we explicitly have got D. Inverse of D is just the inverse of each of the elements on the main diagonal. So we've got D minus 1 explicitly. We can multiply it by B, and it's still a cheap numerical operation. So we can explicitly build matrix BT D minus 1B, and it's got nice numerical features. It's symmetric, it's positive defined, so all conjugate gradient methods, etc. will work. You can even find very, very efficient preconditioners for symmetric and positive defined matrices. What does this term represent?
The divergence of the velocity.
Exactly. This term represents how divergent your current velocity approximation field is. If it's 0, then you have already fulfilled the divergence-free condition, and 0 right-hand side for the linear system means 0 solution vector, and that's true. This means you don't need to make any more updates to the pressure correction. Because the final step in the procedure is just update P as P star, where you would say, here's the trick, because you would say plus P prime, not plus alpha P prime, alpha being under relaxation coefficient. Under relaxation needs to be lower than 1 to make the whole procedure stable. And what happens next? Well, P, unfortunately, P prime is P unfortunately is not the real solution to this problem. Why is it real? Well, because you've done this approximation. You didn't solve with matrix A, but with matrix D. So you take this updated P, and you say, okay, right now my updated P becomes P star, and you start the procedure again, and you do it many, many times until it converges to the reasonable solution. One more final comment.
Okay, so when we compute the P prime, then we compute the U prime also, and also update it with the under relaxation.
You mean if you do something like that?
Yeah.
I don't know how it's implemented, for example, in ANSYS Fluent, because I know there's under relaxation parameter both for pressure and velocity in ANSYS Fluent formulation. I don't know how it's done there. Just see that once you've updated the pressure, you can simply use this equation to generate correct velocity, well, you know, as far as your P is correct. So I would rather use this one to...
Okay. But anyway, you need the new velocity for update the A matrix.
Yes, you need.
Okay.
Questions? First, are the residuals we've seen on Fluent U prime and P prime?
No, they're actually, I think, the residuals of the equation.
Yeah. In Fluent, you would see residuals for Vx, Vy, and continuity or mass. Anyway, it's like it's the residual of that equation.
So your latest U star applied to this equation will give an imbalance between the left-hand side and the right-hand side of the value of the residual. That's the residual.
Yeah.
And you're trying to minimize it.
Okay. And you need to remember that, again, the discussion of the nonlinear convective term applies here again. So once you've solved the linear system of equations, you need to update the velocity and you need to update it in the convective term. So your A matrix will change. And certainly Fluent does calculate the residuals once the matrices are already updated and given, and you got the current pressure and velocity field.
Okay. And how do we have the good results by taking only by the approximation of A equals D?
It converges.
It works.
That's why.
We throw the half of the matrices, but it works.
But only in one of the two problems. It was like only for the pressure correction.
Yeah, exactly. See, maybe it's not evident, but that's right. You didn't get rid of any terms when calculating the velocity out of pressure. You got rid of these terms to calculate the correction of pressure. So maybe you need to, if you didn't get rid of it here, you would just calculate the pressure correction once and it would be correct, the pressure correction. Well, but you did get rid, so it's not correct, but you've got some pressure correction. You apply it, but here you've got the proper matrix.
Okay. But A, so we'll have A on the other side. We will not compute A minus.
Yeah, sure. Yes, you'd have A times this, and you would apply some probably GMRS BICG step to calculate, to solve this linear system.
Any idea whether the condition that there is the under relaxation for pressure and velocity must sum to 1 come from? Because I was expecting that this will come about from these equations and I don't see it.
No idea. No idea why these both should sum up to 1. Absolutely no idea. I would even say more. Once we have written the tutorial for the Quickersim CFD toolbox with a simple algorithm, we are not using under relaxation factors like 0.6 or 0.7. It's rather like 0.02 or something like that to keep everything stable. So this, I don't know, this might also be that ANSYS Fluent uses somehow its own definition of the under relaxation parameters multiplied by something. I don't know.
Maybe it uses it during the computation of the corrections, and maybe that's why it's, but like it's just waiting.
Yeah, don't know.
I was expecting it to just become evident in this analysis you were doing, and I just don't.
No.
There are also many modifications of the simple algorithm name.
Yeah,
Simpler. There are many of them, so we are not even sure if ANSYS Fluent use pure simple, or maybe they
Or ANSYS Fluent simple.
Yeah.
That might not be that simple.
And in that algorithm, that might
I mean, in Fluent you specify which simple algorithm it is. You have simple and simplex. Yeah. But uninvolved default residuals for pressure and velocity are 0.3 and 0.7. You know, per indicator, they're supposed to sum to 1.
Yeah, and the difference is like, I guess it adds some additional method for the skewness correction in simplex. So, like, I think there will appear only like some term in this derivation.
Okay, just a very, very short remark at the end of our discussion is that approximating U by D, you can also be thinking about that as applying a preconditioner of the A matrix in the linear solver. So when the lecture on the linear solvers comes, you will probably get to know a bit more about preconditioning and the idea of preconditioning. Also, what you should remember is you got the simple algorithm requires solving the pressure with positive, symmetric positive defined matrix constructed this way, and the quickest, the best algorithm with the highest convergence rate for any number of unknowns is what currently? Algebraic multigrid. Algebraic multigrid is a concept that, well, we'll see. Maybe we will cover at some point in the future. It's not planned for this course now, but just remember that direct solvers are one group of solvers. The iterative solvers, like based on the Krylov subspace, like conjugate gradients, biconjugate gradients, stabilized, GMRS, probably MinRes also. They are iterative solvers based on the Krylov subspaces. There is also yet another class of solvers based on the concept of algebraic multigrid, and the algebraic multigrid comes from the observation that if you've got a 1D fine difference mesh and you want to solve, let's say, a heat conduction problem, and it looks like that, for example, and the very naive explanation of the concept of the multigrid method, not algebraic multigrid method, is, well, if you take a coarse mesh, you got many less unknowns in the system, and you would still come up with something that probably looks like that. Well, not bad. Already not bad with very few unknowns. So we need to find ways how to propagate the, well, it's like waving hands, really. I just want to introduce the concept. It's like, let's find a way to take this solution from the coarse grid and to use it as a general shape for our fine grid solution. But then we need to find a way how to properly adjust these values here to represent the local solution. But there are ways to do that. Like, it turns out that the classical iterative linear solvers, like Jacobi, Gauss-Seidel successive over relaxation, they tend to smooth out the error here very quickly. Whereas once you reduce the system to very few unknowns, you can use like conjugate gradient on very small linear system, or you can even use Gaussian elimination or backslash operator, because you probably have got 500 unknowns and you can solve it really quickly. But then you need to propagate the solution back to the fine grid, and that's the multigrid concept. The algebraic multigrid is the extension of this concept because you don't need to build the computational mesh explicitly, but algebraic multigrid attempts to figure out these dependencies based on the entries in the matrix. Yeah, question.
Okay, because in the simple algorithm, we still solve that version of our equations with the equation that states that the divergence of velocity field is 0, and we just made a different attempt to solve this. And what if we replaced that equation that states that divergence of velocity is 0 with Poisson equation for pressure, and this would eliminate that 0 term in that matrix, and is it possible to do so, and how would it look like?
I don't know, but I don't think so. I don't think so comes from the observation that if it were possible, people would have already done that.
I'm aware of that.
To be honest, this one is extremely similar to the Poisson equation for pressure, really. This one. Yeah. It's a symmetric positive defined matrix, which is extremely similar to having the Poisson equation for pressure, but we have derived the right-hand side from this whole substitution, etc. Right now, I don't know if it's possible to replace the, I mean, if you generate the pressure Poisson equation for the unsteady Navier-Stokes equation, then it's probably possible because it's how you do the splitting in such schemes that exploit pressure Poisson equation. The problem is that I cannot give you the proper proof or derivation right now, but I remember that you can develop a proof of convergence of such a splitting scheme to the right solution if it's an unsteady Navier-Stokes case, because it really monitors, the proof really monitors how the norm of the divergence field is updated or how it develops. And you can show that it's under control of the steps, time step size. If it's not an unsteady case, and simple algorithm does work for steady states also, then I don't think you can properly formulate the pressure Poisson equation.
Okay, I understand. Thank you.
But I don't think it's not, proof.